I want to now work through three story problems where the way to solve them is you have to use logs. And you're going to see in each of these problems, we get to the point where we have an exponential equation, and the variable we're trying to solve for is part of the exponent. The only way we can get at that variable in the exponent is to use the power of logs. So the first problem I'm going to work is number 56 out of section 5.4 in the book. So once again, section 5.4, let's look at number 56. This is similar to homework problem you have, and it says the radioactive bismuth isotope 210Bi disintegrates according to Q equals, so let me write this down. So it says this chemical, this isotope, it disintegrates, it decays according to this equation. Q equals K times 2 and the exponent on the 2 is minus T over 5. It says where K is a constant and T is the time in days. Express T in terms of Q and K. So basically, they've given you this equation and they're asking you to solve for T. And you look and you see T is part of the exponent where the base is 2. The way we go about solving problems like this, first step is get the exponent term by itself. Right now we have K times 2 to the minus T over 5. I want to move that K or get rid of the K. So I'm going to divide both sides by K. So I end up with Q over K equals 2 to the minus T over 5. Now, one of our rules that we learned about logs is let me write it like this, sorry. If we have a log base A, and then I'm taking the log of an exponent with also base A, an exponent of x, if I do that, it equals x. So you know what I can do? Since here I have the base, my exponent is 2 to the minus T over 5, I can take the log of both sides of this equation, log base 2, and then we'll see what happens. So log base 2, and then log base 2 of 2 to the minus T over 5. And this exponent rule or law says if I'm taking log base 2 of an exponent and the base of my exponent is also 2, the right-hand side ends up equaling just the exponent. And that's the power of logs. I now have a way to sort of free this exponent and for it to become a normal term which I can get at. So if I were to solve for T, I'm going to multiply both sides of this equation by minus 5. So then I have minus 5 log 2 of Q over K equals T. And now I have solved for T. And that T was originally in the exponent, but I was able to get at it by using logs. And that's how you end up solving these kinds of problems. Let me look at it two more quickly. Number 63 says U.S. population growth. The population N of T in millions of the United States T years after 1980 may be approximated by the formula N sub T. All right, let me write it down. So N sub T is the population of the U.S., and it can be approximated by this equation, 231 times E to the 0.0103t. And now they say something important. They say where t equals 0, when the year is 1980. It's almost like 1980 is when the clock starts ticking. That's year 0. So they're saying, how long will it take for the population to double? Now what's interesting is, this is like an exponential equation. This 231 you can think of as N naught. That's my initial value. What this is saying is, the population in 1980, which is T0, is 231 million. That makes sense, because if I set t equal to 0 inside that exponent, e to the 0 is 1, so the population is 231. So now it's asking me, how long will it take for the population to double? So if the population began as 231 million, now I'm looking at when will the population be 462. 231 times 2 is 462. So now I put that into this equation and say 462 equals 231 e to the 0.0103t. And I'm now trying to solve for t. First thing you do is you get the exponent by itself. I'll divide both sides by 231. When I do that, I get 2 equals e to the 0.0103t. I need to solve for that t. It's right now in the exponent. How do I get at it? I'm going to take the log of both sides. And in this case, since I have my base and my exponent's e, I'm actually going to take the natural log of both sides, because when I take the natural log of e to an exponent, when it's all said and done, I just have natural log 2, and this thing is just going to be .0103t. Now if I solve for t, I divide both sides by that 0.0103. So I have natural log of 2 over 0.0103. And I definitely have to get out my calculator. And I can go to my calculator, and I have my natural log key, so I press in 2 and the natural log and divide it by 0.0103. And it equals 67.3. So that's years. I have to add that to 1980. So basically, we're saying approximately in the year 2047 is when the population will double. All right, so the whole key to that is to be able to use logs to get at the exponent.